morning. Welcome to, look, a sunny day in California. What do you know? Welcome to this week's iteration of the CS. I am loud enough. To this week's iteration of CS Seminar. Yeah, as always with Saurabh, it's a great pleasure to introduce him. This is Professor Saurabh Bagchi from Purdue. If you don't know where it is, think middle of the country, Indiana, West Lafayette. That's where it is, about an hour or so from Indianapolis.
I have a slide on that.
Oh, okay, never mind. He'll geolocate himself. Since nobody wants to hear the usual accolades that you talk about speakers, and I've heard a lot about myself, so I'm really tired of this, but I'll tell you this. He is a very prominent and very well-known member of the research community, straddling areas like CPS, security, fault tolerance, dependability, etc. And it is my pleasure to welcome him at our seminar. So without further ado.
Thank you, Dean. Good morning. My name is Saurabh Bagchi. I'm coming to you from Purdue, and I suspect that many of you may not know where it is, so I do have a slide exactly telling you where it is and what you're missing being in sunny California. I lead a center there called CRISP and recently started an institute there funded by the Army Research Lab called A2I2, so I'll tell you a little bit about that. So the work here that I'm presenting is being done as part of the center CRISP, which has about 35 faculty now affiliated with it in 3 different thrust areas: cyber systems, cyber physical systems, and socio-technical systems. And sort of the underlying theme of all of this is resilience, broadly defined. So how do you create resilient cyber systems, resilient cyber physical systems? And because many systems have a mixture of social elements and technical elements, how do you also build resilience into those kinds of systems? The center involves faculty from both EC and CS, and also several of the other engineering departments that we have. And then the Army Research Lab's Assured Autonomy Innovation Institute. This is something that started toward the tail end of 2020, and then has been going on. It's a 5-year institute. Hopefully, if we do a good job, then we get 5 more years. And that is looking at different aspects of security for distributed systems, and here the specific kinds of distributed systems that they're interested in is these IoT and embedded devices. So how can you make these devices function more and more autonomously rather than being what they are today, sort of the dumb eyes and ears of these systems? And of course, if you want to make these work more autonomously, you have to worry about how do you make them work autonomously while protecting the security and the privacy of these devices and of the data that they are creating. So again, some of the work that I'm going to present here has been done as part of this institute, and which is 6 faculty members who are PIs, co-PIs on it. And here is that slide, which is where I'm coming from. Some people charitably refer to it as the middle of nowhere. It's about 2 hours from Chicago and about 1 hour from Indianapolis. It's an old university. This is what it looks like on a sunny day like this, and hopefully I have my group of about 20 which are working very busily while I get to visit all these nice places like Irvine, and they're so situated in this building right here. And now to tell you what you're missing because you are in sunny California, you will never get to experience this. You have to get to the Midwest in order to experience this. And we don't have many hills, so we just make do with whatever we can in order to slide down on these hills. So if you come into our place December, January, February, chances are pretty high you're going to get to experience this. All right, so the presentation is divided into 2 broad phases. The first phase is a broad-based discussion about what dependability means, what dependability and data analytics really mean. So this is a high-level discussion. Jean had prompted me that this is going to be a fairly diverse audience, so I took time to create this, which is going to set the stage for it. And then to convince you that I just don't talk about high-level pretty pictures, I do have the more detailed talk, which is about how do you auto-configure distributed systems in order to ensure dependability and how data analytics plays into this. And I do want to spend some time talking about takeaways and what are the open problems in this space. Lots of smart students in here, and hopefully some of you would be able to solve some of these open problems. And throughout this talk, I encourage you to stop me, challenge me on any of these points, ask me questions. Anything but deathly silence in the room is appreciated. Okay? And I don't expect to finish all the slides. In fact, if I do, that means it's a very bad talk. Nobody's been paying attention. So please stop me. All right. So the basics of dependability, what does dependability mean? What it means is you want to build systems that would be able to provide their relevant functionality despite the occurrence of these different kinds of unexpected situations. So they would be able to provide the right kind of functionality despite the occurrence of natural errors. And these natural errors may happen either in the hardware or in the software or in the interface between them. They also have to deal with security errors. So the word dependability really brings in both natural errors and security errors into it. And when you're talking about security errors, you have to think about errors which are maliciously introduced from external to the system, as well as errors which are introduced by insiders in the system. So those are the two broad classes. So these have been classic threat models, failure models that the dependability community has dealt with. A threat model that has emerged and become more and more important over the last 5, 6, 7 years is this one, which is these unexpected interactions between the humans who are working on these systems, operating these systems, and the hardware software of these systems. So a system which is built with the best intentions but does not take into account all the possible unexpected interactions that may happen with the humans is going to have dependability outages. So there is a growing understanding and a growing realization that dependability also needs to include this class of fault model or threat model. And here is a simplistic view of how dependability is accomplished. This is true in individual nodes, in single node systems, as well as in distributed systems. So this is by design a simplistic linear view of it, almost linear view of it. So you try to prevent these kinds of errors in the first place as long as you can. So you design your hardware, software, you design for all possible kinds of interactions that may happen. So prevention, of course, is the best strategy. But best prevention strategies still leave open holes in there. So then what you want to do is as soon as this error becomes a user visible failure, or even before it becomes a user visible failure, you want to detect that there is a problem. Once you detect this problem, then you could do one of two things, or maybe you could do both of them in parallel. You could try to contain this error. So you want this error not to spread out and affect your overall system and create a large-scale outage. But you want to contain this to small functionalities within your overall system. In parallel, you may want to do root cause analysis, or what's called diagnosis, in order to understand which are the components which were the root cause of this problem, where the cascade of these errors really started from. So that's the diagnosis aspect of it. And then once you're able to do good diagnosis, good containment, in a fairly limited set of cases, you could do automated repair. So you could reconfigure your system, you could restart your system, get it back to a pristine state where you don't have this kind of a problem. Oftentimes this repair leads to a degraded mode of operation, but especially in mission critical systems, you are able to still continue functioning. So that's the overall view of how dependability is achieved. And now let's look at two emerging trends in this community. And when I say emerging trends, if you went back 10 years, the leading conferences in the field would hardly have any papers which address this. If you look at the top conferences in the field today, the top security conferences, DSN, middleware, and so on, you would find that these two trends have become quite important. So the first trend that you have in here is that the execution environments are changing. So back in the days, execution environments were all homogeneous, same kinds of nodes, same kinds of networks, and all the components that were running on these homogeneous nodes and networks were developed in-house, which means you had near perfect understanding of these components. You could do whatever kind of static analysis of these components, and you just had the human element which understood how these components were architected and configured together. To the brave new world of today, where these systems are increasingly made up of third-party software components. So you as the system designer, system owner, are putting together the system using components which have been developed by many, many different parties. So obviously you don't have full understanding of these components. And increasingly, in a larger number of cases, you don't even have observability of these components, meaning you couldn't go in and inspect the internals of these components. You couldn't run your favorite static analysis on them in order to understand what are the weak vulnerabilities and dependability weak points in them. And the related aspect to this is they are running on heterogeneous nodes and networks, and I'll have some examples of this. The second trend that's been really emerging is that these solutions have to be dynamic and adaptable. So back in the days, the dependability solutions were essentially rule-based, and they were static, meaning this is the rule that's going to be enforced at all times, and these rules are not changing. They're not changing as a function of the workloads or applications, and they're not changing as a function of the conditions that exist in your system. Whereas in the brave new world, these solutions have to be data-driven themselves. So you have to learn and continually learn what these rules are, which tell you if there is an error or not, which tell you what is the root cause of the problem. And the learning has to be conditioned on the workload or application. What is the system condition? Means how loaded is the system, what kinds of applications are coexisting in the system, and they have to be dependent on the architecture. Are you running it on an FPGA or an ASIC, or what kind of a GPU or what have you? So that's the second trend that's there. And here are two examples which show what I mean by these two. One is, this is the execution environments are changing. Any guesses what picture we are looking at here? Yes? Somebody just needs to shout out louder. So this is one of those supercomputing clusters, which was the top #1. Oh, so IBM you can see in here, so that was an easy answer. This was deployed at Oak Ridge National Lab, was #1 on the supercomputer list. And every single node in here is exactly identical. Every single node is connected via exactly identical interconnect. So this is this notion of homogeneous systems, where nodes and networks are homogeneous, to where this is from one of our recent papers, where you have this 3-tier hierarchy, and your application may opportunistically run on any part of this 3-tier hierarchy. So what you have here is the edge of the system, where you have your mobile device or your embedded device or your IoT device, which are constrained. What you have here are these edge servers, which are still constrained but less so. And then here you have your traditional data center servers. And they're connected via different kinds of wireless networks as well. So this kind of an architecture has been known now for several years. There are many, many research papers on this. What the community is slowly trying to come to grips with is how can you run your applications in an adaptable manner where it can really float between any parts of this layer, and this is critical, and you're able to achieve the reliability and the security that you need. So this is an example with the execution environments are changing. The example of a static to dynamic, this is your very simple code where you've written some function to calculate the square root. You assert functions. So this is asserting that the input is greater than equal to 0. This is asserting that the value that you computed indeed is the correct square root. Here is something from one of our papers where you're looking at a cloud application, and you're trying to decide when I should move a virtual machine to a different physical machine. So here is an example of a static rule. The CPU load is greater than 80% or the memory occupancy is greater than 90%. That triggers this kind of an action. Okay? So this is an example where you have a static rule which is enforced all the time. To something which is, this is from our New RIPS 2020 paper, is here you're trying to do outlier detection. So let me give you the context for this. So we have, through a large center scale project, a very large IoT deployment in digital agriculture fields and in manufacturing facilities. So these IoT nodes are sensing all different kinds of things like temperature, pressure, audio signals, and so on. And you're trying to make certain decisions based on it. For example, is this manufacturing pipeline running too slow? Or in the agriculture space, is the right level of nutrient concentration being put in there? So there are sensors, actually quite specialized sensors, which are in the ground, measuring things like nitrate, potassium, and so on. Stuff that I know very little about. I just know what the signal that's coming out of it. Now, being academics, we had to invent some problems. So the problem that we invented is what happens if some of these sensors get compromised? So we thought this was a completely make-believe problem. and try to solve that. But then once we had this deployment out there in the field for many, many, many months, we found that some of these kinds of failures were happening, not because anybody was maliciously trying to break into these, but because of just the natural errors. So this is a famous saying from Amazon bigwig saying if you run this system long enough, then the worst kind of security failure that you can think of is going to happen even without a security failure. Meaning just by the luck of the draw, you are going to have three things fail at the same time. So here what we're trying to do is try to detect if a particular data point is an outlier or not. So then you can throw out that data point and make your inferencing based on the inlier data points. So the simple static way of doing it would be to say, okay, here is my distribution for clean data, and any value that lies outside of this distribution I'm going to say is an outlier, and I'm going to throw it out. Okay? But failures, especially security failures, are going to happen in a way that the malicious data is going to be an inlier. So if you look at an individual data point, it's going to fall within the distribution. So what's the way to get around that? The way to get around that is don't look at individual data points and assert this rule. So this would be an example of a static rule. If it falls outside this distribution with a certain probability, say it's an outlier. So instead what we do is we create a distribution based on many, many of these data points. And if that distribution looks off, like it does in this red case, then you say that that sensor has been compromised, and then you can throw it out. Okay? So there's obviously a lot of math details and different kinds of threat models that this needs to address, but the point I want you to take away from this is a simple static rule-based solution is increasingly not feasible, whereas you need to have this kind, where we even learn what is the shape of this adversarial distribution versus the benign distribution. All right, I've thrown quite a bit at you. It's still high level, but I want to pause and see if there are any comments or thoughts. Nalini?
You know, I think you might get the data and analyze that perhaps there's a failure in a particular sensor, but a lot of these systems that are out in the field are often full stack solutions made by proprietary manufacturers with their own devices, their own networks, their own servers, cloud. That some of our experience has been that.
Right.
So in that case, I think looking at the data and trying to assert what is useful and not useful and what is an inlier, outlier is nice. But it's often difficult to detect where the problem is happening. It may not be the sensor.
Right, right.
It could be somewhere else.
Yes.
And so the question is, maybe it's coming up as you're going on.
Yeah,
The problem could occur anywhere from the phenomena to where you're interpreting it, because
Right.
either the technique is imperfect, the network is imperfect,
Right.
something got lost, delayed.
So you're exactly right. So this gets you localization to the point of an individual node. So when I said simplistically that the sensor is bad, not the physical sensor may not be bad, anything in that software stack may be bad, right? But it's at least a start from an IoT network deployment of 100 plus nodes. Now you say, go in and look at what's happening on this one particular node. And curiously, we have a paper in URIPS accepted for this year, which is doing root cause diagnosis within a particular node. So think about one node's software being built of many, many micro services. So then this root cause analysis technique can go in and say microservice 1 is most likely, 5 is the next most likely, and so on. So that relies on being able to observe the interactions between these microservices. So it's still not black box, it's sort of gray box, but we don't have to look inside a microservice to be able to do that. So, so the punchline is this is not the right way of doing it, this is the more modern and more accurate way of doing this kind of anomaly detection. Any other thoughts? Question?
Going back to your previous slide, yeah, I was wondering when you mentioned floatings, what did you exactly mean by that? So is it like client server?
So what I mean is so there is one way of doing it which has been published in the Mobis census world going back 4 or 5 years, is you take your application, you partition it, and you say this partition will run here, this partition will run here, and this partition will run here. And increasingly in a data-dependent world, we find that that static partitioning is no longer sufficient. For example, the same application, maybe it's a very crowded scene, so you cannot do anything in here. You have to do things at least here or here. So that's what I mean by floating.
Thank you.
All right? So now I'm going to take a view of dependability, which is going across the stack. So, and somewhat simplistically, I have broken this tag down into low-end embedded devices, mobile wearable devices, clusters of edge devices, then the traditional data center clusters, and something which overlays all of this is autonomous systems which are built out of all of them. So the high-level way of framing this problem is, for each of these layers, you're going to have some problem context which is specific to that particular layer. So if you look at, let's say, the wearable and the mobile world, the problem context is you have new kinds of failure modes that are emerging because you have the wearable. So the wearable that I have, for example, doesn't allow me to do lots of rich human user interactions as a mobile device, or definitely as a traditional computer would do. And this leads to new kinds of failure patterns. There are new software design patterns that have come in for wearable software because of the simple fact that you have much less real estate in order for you to interact with this, much less real estate for you to monitor what's going on with these devices. And then you have crowd sensing of information through many, many mobile sensors, since we are all carrying with us these hugely powerful and sensorified devices with us. You could put all of this to good use. So that's the problem context. Now, each of them comes with a set of domain-specific requirements. So the requirements that we have here is individual devices in this context are not going to be reliable or secure, and you have to build a secure or reliable system out of many, many of these insecure and unreliable devices. And this is to be largely unobtrusive to human users. So you cannot expect a human user to interact with these devices to tell what is right, what is wrong at any degree of frequency. So this is to be largely unobtrusive to the users who are wearing them or carrying these devices with them. Now, I'll give you a very high-level snapshot of some of the most important results that have come out, and specifically my domain is data analytics in order to ensure or improve the dependability of systems in this layer. So we now have a better way of understanding human interactions in a reliable, secure manner. There's a lot of work going on, and these are quite sensitive devices in the sense that they're collecting sensitive data, personalized data about us. How can I make useful deductions even while protecting the privacy of individual data? And then how do you do reliable inferencing from a lot of this data? But as I said, individual data points are likely to be failure prone, either because of natural failures or because somebody's maliciously trying to bring down your system. So there have been some notable success stories in each of these. Moving up in this layer, if you look at the clusters of edge devices, the problem context for dependability here are the edge capacity is not fully elastic like you would have in a data center. What do I mean by that? So does the word elastic mean anything to you? When I say my data center capacity is elastic, what do I mean?
Auto-scaling?
Exactly. So that means auto-scaling. So if my application's footprint increases, I can easily spin up more number of virtual machines and ease the load through that. When you're talking about clusters of edge devices, you don't have that level of elasticity. The individual edge device availability is highly variable. They may come and go. They are large geographic scale. They're spread out over large geographic areas, and there is increasing amount of heterogeneity in there. So that's the problem context. So the requirements for any solution that uses edge devices are that the reason I'm going to edge clusters instead of data center clusters, or in addition to data center clusters, is because I really care about low latency. I'm talking about sub 10 millisecond latency. So I cannot put a very heavy duty protocol in here which is going to blow that latency budget out of the water. I have to be very conscious about the latency budget. And something that we have just introduced into the community, and now it's beginning to get more traction. So for example, we work with AT&T who have these managed edge devices. So every AT&T base station acts as a managed edge device. So they can offload computation onto these base stations. But in addition to these managed edge devices, you also have lots and lots of unmanaged edge devices. What do I mean by unmanaged edge devices? So these are devices that you and I are carrying with us, or that may be there in an infrastructure like a classroom, to which I can opportunistically offload some computation. So there's a lot of work on opportunistic offloading onto edge devices, but this world where you have a mix of managed and unmanaged edge devices is sort of a brave new world. They obviously have different kinds of failure modes and different kinds of security modes. Managed edge devices are much more likely to be reliable and secured than unmanaged, but they cost money. So how can you live in this world where there is this mixture? So I think three important classes of results that have come out in this space is How can I approximate demanding streaming machine learning algorithms to run on these edge devices? A lot of work in the database world as well as in the machine learning world. How can I do this hybrid offloading? This is this notion that we were discussing of floating application which can float between multiple layers. And how can I do streaming inference under adversaries? Inference under adversaries has seen a lot of work, but now I want to do the streaming inference on data that is not at rest, but it is flowing through my overall system, and I want to do this with adversaries. Question, team?
Yeah, I was wondering if you looked at the economic side of this. Like, under which conditions does it make any economic sense to pick, let's say, clusters of edge
Yeah,
devices,
actually
managed device, as opposed to a much faster data center, you know,
Yeah.
maybe a higher propagation delay, but much faster computation.
So if it's a throughput intensive job, then it doesn't make sense for you to do this. It only makes sense if you have latency sensitive. And even within latency sensitive, if you just take the standard algorithms and put them in here, it will just not be feasible.
Well, let's
It will
say
just
video
not run.
conferencing.
Yeah, video conference.
Would it make sense to
So-
put any of it in?
So we have a paper in Census, for example, going back 2 years, which shows how you can approximate in a very scientific, rational manner so that you can squeeze it down and you play in this three-dimensional space. Accuracy is one dimension, latency is the other dimension, and energy is the other dimension. So many of these devices allow you to have different energy modes as well. So depending upon what your energy budget is, you can set the energy mode. You can either run it at full blast or you can dial it down. And this paper of ours looks at the economic question, but this is a much broader question. We are not economists by training, so this answers a very simplistic view of that. It asks a whole set of people, is what would it take for you to be part of this kind of an unmanaged edge system? And answers it to some degree.
So possibly another reason may not just be speed, latency versus cost. It could also have to do with where the trust boundaries lie.
That's right.
Right?
Privacy,
So,
yeah.
so the edge could be within that trust boundary, and therefore there may be a valuable reason why you want to keep things.
Or exactly the opposite.
Or exactly the opposite.
Yeah,
You may not trust the edge.
yeah, yeah.
It depends on where it is.
Yeah, that's exactly right. Yeah, we hear that increasingly where people are territorial about their data. This often appears in the federated learning context where they say, my hospital data doesn't leave my hospital premises. I still want to benefit from the learning that's happening across these 100 hospitals, but my data has to stay private to me. Okay, in the interest of time, I'm going to skip over this. Now let me leave with one final high-level point. We are halfway into the talk. Is this notion of dependability by design and dependability by reaction. So dependability by design, so this is an emerging sort of, maybe it's now quite well accepted in the community that this is one reasonable way of framing your dependability design, is you try to build into your design ways to handle different kinds of errors, failures, security attacks, okay? But you're never going to cover 100% of the cases. Therefore, you also have to be very agile in order to do things reactively. So once your system is up and running, once your application is running, you're going to see new kinds of failure modes appear, and then you have to very quickly adapt to them and be able to handle them. And when I say handle, it could mean detection, it could mean containment, it could mean diagnosis or recovery. 4 of those blocks which I had in an earlier slide, okay? So both of these aspects are important. So this is a realization that sort of came to the community maybe 4 or 5 years back. And then something which is very recent is this loop, whereby once you're able to react to something, can you now bring it earlier in the design process and build it into your system? So why would we want to do this? Why isn't a union of these two good enough? Why do I want to move some techniques from here to here? Because it's typically more expensive to do this than to do this in terms of time. So if you're trying to get your system to be up and operational most of the time, you don't want to do too much of this. You want to build as much of it in the design process as you can. So this is somewhat of an abstract thing. So to give you one concrete example of this, so this is from our security and privacy paper this year, which asks this simplistic looking question is you have a large scale critical infrastructure system and you want to make security investments in various parts of your system. And for obvious reasons, for any large scale legacy infrastructure, you cannot invest in protecting every single asset that you have in the system. So this is the cartoon view of the world. Let's say this is the target asset that you want to protect in your system, and this is the starting point of these kinds of attacks. In realistic systems, there are going to be many VTs and many VSs. Okay? But you create some kind of an attack graph model which says all the different ways in which you can start, the bad guy can start from here and compromise these. So you as a defender are responsible for putting in security investments in these various edges. And when you put a security investment in an edge, it doesn't necessarily disconnect that edge, but it reduces the propagation probability from one node to another. Okay? So that's a simple framing of this. So the learning part that we show off in this paper is, we learn that the optimal decision under a fairly wide set of assumptions is to determine what the min-cut edge set is in this attack graph. And if you've forgotten this term, you should take your algorithm class again or look at your notes. It just means it's a minimum cardinality set which is going to disconnect the VS from the VT. Okay? So you learn the min-cut edge set. Then you invest in the security protections on all the edges in that min-cut set. So for example, here your min-cut set could be this and this, or this and this. And then this is the hardest part of it, is it's not a 0-1, your security investment. You have to determine what is the right level of security investment that you put in these edges. And the right level depends on a whole variety of factors. What is the probability with which it goes down as you make security investments? And if you could do this, if you could learn all of this, then you'll have very good protection preventing a VS to reach VT. So this is a simplistic example of where learning while your system is operational, is deployed, helps you in making your systems more dependable. And that's the last high-level slide I have. So I'll give you a taste of some of the lower-level work that we've done, but let me pause there for a minute and see if there's any thought or question.
What is the attack graph you just mentioned?
Say that again?
What is the attack graph you just mentioned?
What is an attack graph?
Yeah.
So an attack graph is a very widely used conceptualization for how an attack can spread in a distributed system. The basic semantic is, if I reach V1, then with a certain probability I can reach V3. But from VS I cannot directly reach V3. So there's a whole literature in how do you create realistic attack graphs and how do you keep updating them as your system gets updated. All right, so here I'm going to talk about two aspects, and I think only touch upon briefly on them, and for all the gory details you can look at our papers. This part, you are my guinea pig. I'm trying this part out first with this is the first audience when I'm trying this out. This part is earlier work, but this has been well taken up in the community. And I do want to spend some time on the takeaways and open problems. So this part is talking about how do you auto-configure an application for the cloud. So here is the problem statement, and this very wordy slide, you don't have to read all of it, but what it's saying is that if you have a distributed application, any distributed application worth its salt is going to have many, many configuration parameters. And when you're now putting these distributed applications on the cloud itself has many configuration parameters. What kind of virtual machine instance do you want to run this on? What kind of networking ability do you put between these multiple virtual machines and so on? And the appropriate configuration is important for guaranteeing this trade-off between performance and reliability for your application. Okay? So this is problem 101. Problem 102 becomes, now if you're talking about stateful applications. So stateful applications mean that when this application processes request 1, it generates some state. When it processes request 2, that request 2's response may be dependent on the state that was generated earlier. So stateful applications in general are harder to handle than stateless applications. So stateful applications, and the canonical example of a stateful application is a database. So today increasingly databases are sitting in the cloud, and various surveys show that most of the database administrator's job today is how do you configure your databases as your application parameters keep changing. So there's a very large parameter space for this, so of the order of 50 plus parameters for a leading NoSQL database, and then the cloud parameters are of the order of a few hundred. So you can easily visualize the combinatorial complexity of this. And this problem is also challenging because there's oftentimes the changes in the workloads. So if your workload was static from the beginning of time till the end of time, then it's one problem. You do it once, you pay your database administrator, your cloud administrator, and you're done. But in reality, those are also going to be changing. So the high-level problem here is, can I automatically find out the best configuration for a given workload? And can I do it fast enough as your application or workload is changing? So this is just talking about the large configuration space. And oftentimes what the metric that I'm trying to optimize for is performance normalized by the dollar. So what could performance mean in this case? It could mean latency. It could mean throughput. If you're reliability conscious, it could mean your resilience. I'm able to tolerate n number of concurrent failures in my system. So those are your performance metrics. They always have to be normalized by the dollar cost, because you can typically throw more dollars at it and create more performing system in here. So the key insight that we brought in, now going back 2 years, is that you need to have a joint optimization of your application configuration space and your cloud configuration space. So it's not enough to individually optimize your application, your database, your key value data store, and your cloud. It's important to do a joint optimization. And here is an example of this. So if you use this m4.large, which is a kind of virtual machine, then the optimal cache size of Cassandra, which is the NoSQL database, is 8x that if you use this with C4.large. Right? So it shows that your cloud parameter also changes what is your application parameters. And larger sized VMs do not always provide you with the better performance per dollar, because you may be over provisioning your system. So the dollar cost may be too large for this. Okay? So when we came into this picture, it was an open problem, and I think it still isn't, the broad problem has not been solved, is can I automatically configure for the best performance per dollar? So here is a motivating example, which again shows that depending upon what your cloud size is, your throughput can of course vary, but the best application configuration, the worst application configuration also has a spread, which is again motivating that you need to optimize the cloud configuration type and the database configuration type together. Okay, so the other aspect of this is that you need to online reconfigure these kinds of systems. It's not enough for you to come up with the best, the optimal strategy statically and stick with it. You need to do this because your application characteristics may change, and also importantly, your reliability requirements or your performance requirements may evolve over time, and therefore the dynamic configuration is needed. But so you may say, so what? I can know what is the best configuration for a given application characteristic, for a given requirement, and whenever these change, I'm going to stop the world. I'm going to say, let me reconfigure this, and let me bring back the world. So what do you think would be the problem with that? The big problem is that oftentimes these are not lively reconfigured systems. So you need to bring the world down, reconfigure it, and bring the world back up. And whenever you're talking about stateful applications like a database, then a restart would mean that you have made your system unavailable for a certain amount of time. And importantly, the workload changes can be transient, and therefore this cost of reconfiguration may not be recouped over time. And here is an example. But you may be thinking that this is a bait and switch. I told you all about this dependability, and now I suddenly made this switch to reconfiguration. What does this have to do with it? That's because predictability is an important attribute of dependability. It's not enough for me to say my availability is X. I also have to be able to bound what the mu plus minus 3 sigma is. And this kind of reconfigurability gives you that kind of predictability or determinism. And the other is that you also have to guarantee probabilistically latencies for your system. So if you violate that, then that's a dent against the dependability of your system. So I'm going to skip over all this background stuff. So here is a cartoon showing that your workloads are changing over time. And in this simple view of the world, you only have two configurations that you can pick, conf1 and conf2. So when your workload type is 1, conf1 gives you 70 kiloops per second, so this is throughput. When it changes to workload 2, it dips down to 40 kiloops per second. Okay? So you say, okay, conf1 is no longer good enough for me, let me switch to conf2. So when you switch to conf2, now your throughput improves to 60 kiloops per second, but very soon this workload 2 goes away, it changes to workload 1. And with workload 1, conf2 is a terrible configuration to use. It dials it all the way down to 30 kiloops per second. So abstracting out, the problem for you is to decide, when my workload changed, should I switch from conf1 to conf2, or am I better off just sticking with conf1? So what do you think is the answer to that question? What does it depend on?
The future.
Exactly, the future. And none of us are soothsayers, so we cannot know what the future is. So expanding on your point, if I knew the future and I knew that this workload 2 is going to persist for a long period of time, then I can say, yeah, it's worth my while to switch to conf2. If on the other hand, workload 2 is very transient, then this is not worth it. Remember that every time I make a switch, I oftentimes suffer a degradation in the metric of choice. My throughput goes down, my dollar cost goes up, what have you. So exactly, it's dependent on that future. So this is a real example now from the largest database for a genomics production system. This is part of an NIH grant that we have. So this is done in a sandboxed environment, but with that real database. So several things going on in here. So this solid black line is tracing the throughput. And this dotted line is giving you the gain over a static configuration. Static configuration is what people do today. Okay? So this dotted line above 0 means good. Below 0 means your reconfiguration was useless. In fact, it's hurting the system. So this shows that if your workload persists for more than like 340 seconds, then this dotted line goes above the 0 bar. Meaning, then it's worth your while to do this configuration. If your workload would persist for less than that, then you shouldn't do it. Okay, so this is a nice hunky-dory picture, but what's wrong with it is we don't know what the future is. So we have to do 3 things. We have to estimate the future, means how quickly my workload is changing. We have to estimate what is going to be the benefit of making the change. If I do switch from conf1 to conf2, what is the benefit in terms of throughput, latency, whatever? And 3 is, I have to estimate what is the cost of doing the switch. And all 3 of these questions are answered by these 2 papers of ours, which 5 man-years of our work, I will not have a chance to go into it, but those are the 3 broad questions that we answer. And as a result of answering those questions, we are able to achieve this. So the takeaway here is that for cost optimal performance of any stateful application, you have to jointly optimize the application and the cloud configuration. And our work shows that this configuration that you arrive at should be heterogeneous. Meaning in a distributed cluster, let's say you have n number of entities, not all entities should have the same configuration. This may be somewhat counterintuitive, but the essential reason is because I want to support various different kinds of workloads in the same cluster. It's rarely that one system is going to focus on just one workload at a time. And so we show the minimum number of servers to reconfigure we come up with, and the rest of it is really details. But as a result of it, compared to all prior work, we are able to achieve the best performance normalized by the dollar. Okay, so I'm going to go into the second part of my detailed piece. And if you're really bored, you can try out this fun tech quiz. And you can tell me how you score in that quiz. So the second part is looking at a cloud platform called serverless. And the work that I'm presenting here appeared at OSDI this year, was the best paper award at Sigmetrics and ATC 21. And this is looking at the problem of how do I automatically configure a serverless platform. So does the word let's see a show of hands. How many of you have heard of this term serverless? All right, so about 25%. So maybe I will give a very brief summary of this. The most memorable line, which unfortunately I didn't come up with, is if you think of the traditional cloud as your enterprise or Hertz of the world, a rental car of the world, your serverless is your Uber or Lyft of the world. So it's a pay-as-you-go model. So you have a fancy idea for a new cloud application. You don't have to go and rent by the hour or by the month. You can just rent based on exactly how much resource you're going to consume. And this billing can be of the order of seconds. So typical machine learning application, let's say, is you have an input frame that is coming in. You want to classify this and say how many people are there, how many cars are there. Okay? You can write this as a serverless application, which is these different what are called functions or lambdas. So the sequence of functions are executed in this simple word in series. You start here, you end here, you're done. Okay? And you're going to run this on AWS Lambda or Google Cloud Functions, and you're going to be charged for exactly how much resource each of these functions is going to be. Now, a slightly more complex application is where there is a DAG. So you can run multiple frames, let's say, in parallel in here. Okay? And this is supported by today's application, today's serverless platforms. So here, you would have to run 61 virtual machines today in order to have each function be executing on a separate virtual machine. So there are two problems with this way of serverless execution. The first problem is that you incur a communication latency whenever you go from function 1 to function 2. And the way today's serverless platforms work is there is no way of directly communicating between function 1 and function 2. You have to go through some stable store, S3, let's say, for Amazon, and this has to dump it there, this has to get it from there. Okay? So that's performance slowdown. And typically, these serverless applications are meant for very fast operating ones. So something comes in, you very quickly react to it, get your thing done, and move on. So any kind of latency like this is bad. And the second is there is computation skew among multiple parallel paths. So for example, maybe this frame is very complex, so this classify takes a long time. This frame is easier, so it takes a short time, but there is a computation skew, and therefore you have to wait for the shortest one. This is very, very well known in the performance literature. Most of you have come across some variant of this. So what we did is to do this workload characterization from Microsoft Azure. So what we had to do to get these traces from Microsoft is a long story. I had to promise my second-born child almost so that we could get this, but we have it. Now the community can use it. So this is the first workload trace from Azure's production clusters on serverless. So we did an analysis of 2 weeks of this data across 6 different data centers, and we used that to motivate our solution. Okay. So the first problem, the first insight that we have is that if you look at the depth of these DAGs versus the width of these DAGs, the width can be fairly large. You can have up to 11K in parallel invocations. In terms of the depth, they're not that large. The highest we saw was 47. That's observation 1. Observation 2, so observation 2 is with respect to the DAG frequency. So you would have come across some variant of this rule, the 90-10 rule, which is you spend 90% of your time debugging 10% of your code or 10% of the bugs. As a professor, you spend 90% of your time dealing with 10% of the problem kids you have in your class, and the remaining 90% are breeze. And that similar kind of a thing shows up here, except it's 95-5. So 95% of all the DAG invocations are by the 5% of the most frequent DAGs. What that means is if I could optimize that 5% of the most frequent DAGs, then I have a huge gain. Observation 2. Observation 3 is that those 2 factors that I mentioned really hurt you. So the intermediate data size between different functions that you have, as long as it grows large, this can really hurt your tail latency. So not your median latency, but your tail latency. And then DAGs have significant amount of skew, and skew really hurts even your median latency. So these are two observations based, this is the third set of observations based on these traces. So we use this to motivate two design aspects, which I'll just touch in brief. So one is fusion. Fusion means if I have in-series functions, right now this is what happens. What we can do is we can fuse them and we can run them within the same virtual machine, therefore eating in the cost of the data transfer between these. Lots of details for this to work. What is the size of the VM? When do I decide whether to fuse or not? But it works for a large number of these cases. The second one is the bundling. So if you have this kind of a computation skew between parallel stages, what you could do is you could put them in the same VM, but increase the resource of that VM. What does that do? What that does is, once classify 1 is done, classify 2 can take over all the resources that classify 1 is no longer using. So this is a very well-known principle in system design, is you give it larger size buckets, so unused capacity by process 1 can be taken up by process 2. Lots of things that are needed in order to make this work is what should be the right size of the bundle, what do you bundle, and so on. But you have to read our OSDI paper in order to get an idea of that. All right. So in terms of the evaluation, I'm just going to give you a brief flavor of this. So this is a video analytics application. So this is a application that's very widely used for serverless platforms. So video comes in, you split this video in different size chunks, you extract some representative frame from each chunk, you do some processing on that chunk. Let's say you want to classify that chunk, or you want to detect objects in that chunk, and so on. And then you dump it back into your stable storage. So naturally, since this is such a widely used application, there has been quite a bit of work trying to optimize these applications for serverless platforms. But because of those two design constraints of fusion and bundling, design considerations, we find that in terms of the P95 latency or the cost, we win over all of these prior works. And really, we win because we're able to figure out which functions to fuse, bundle, and when. The key point there is that sometimes fusion is going to hurt you, and sometimes bundling is going to hurt you. Or if you bundle too much, it's going to hurt you because your VM will just not have enough juice in order to serve all of these different functions within one bundle. So we win in terms of both the tail latency as well as the cost, as well as the throughput. And another important aspect for any solution in this space is you should be able to specify what your latency target is or what your cost target is. And your solution must be able to adapt to whatever the latency or the cost target is. And we are able to do that through the design that we have. So yeah, the takeaways are, firstly, I think this real-world serverless DAG trace is a very important resource for the community. And then these kinds of design optimizations really help you as long as you can figure out when to do this. And sort of, now let me go on in the last 5 minutes or so into the takeaways and the open problems. And I really encourage you to think deeply and challenge me on some of them if you think you've already solved some of them. So the open problems in this space, and by this space I mean how do I configure a large-scale system which is running on the cloud, is oftentimes my optimal configuration or even semi-optimal configuration depends on the data. It is not divorced from the data. Simple example, if you have a very complicated video frame, you will need some kind of a configuration versus a simple video frame with one object. But cloud providers even cannot see inside your request data. So we thought going in, we are getting the trace from Microsoft Azure, we should be able to see even the data, but that's not the case. Legally, they're not allowed to see the data. They can see metadata, like what is the size, what is the frequency, and so on. So how do I handle data-dependent behavior when I'm not able to look at the data, but I'm able to look at the metadata? That's a broad open problem. The second one is all of these decisions, when to fuse, when to bundle. Another one is what is the right size VM that you assign. These are based on machine learning models, fairly simple machine learning models. And you have to refresh these machine learning models when things change under your feet. For example, your workload characteristics change, or the level of contention that you have in your system change. So when do I refresh the model? Can I do this incrementally so I don't stop the whole world in order to refresh? That's an open problem. And the third one, this is our OSDI and Sigmetrics work showed it for the first time, is I want to support more complex machine learning workloads on these cloud platforms. If it were a single function, I know very well how to do it. If these are DAGs, so more complex workloads, how do I do this? Especially if you have dependencies across multiple requests. So this is this notion of stateful, where request 1's processing affects request 2's processing. Bubbling up to a real 30,000 feet view. So I started this talk with saying data analytics and dependability. So what are some takeaways? So data analytics can help in making your system more reliable, more secure, but there are many caveats. So first is only in some cases. Second is the model that you're employing must be quite simple. So make it as simple as it needs to be, but no simpler. The third is that whatever time you take in inferencing or searching for the best model, you have to take that time into account. Let's say your latency budget is 10 milliseconds. The most baseline way, this would eat up into a whole latency budget, just in searching for what is the best model. And that's obviously not the right way to do it. So you have to take the model inference and search overheads into account. The white box nature of your machine learning models is often a useful property. So you can query it, you can ask what if questions. But in reality, this is rarely the case. Your models are often going to be gray box at best. So you may know this is the architecture, you may know some of your weights, but you won't have full visibility into it. And finally, whatever model you come up with, you have to be agile in order to change it when the situation changes under your feet. It will not be a static model that you can use throughout the lifetime of your application. That's it. It does take a village to do this kind of a work. I have lots and lots of collaborators across government, across industry, and definitely at Purdue itself to thank for this. Happy to take any questions or comments.